The speed of sound. Now, I'm going to demonstrate one method in which you can use to measure the speed of sound, some of the effects of the speed of sound, and a practical application. Let me remind you of the wave equation. Wave equation is a relationship between the velocity of a wave, in this case sound, with a speed, to its wavelength and frequency. Now, I bring this up because once we are able to figure out the velocity of sound in the air, it kind of unlocks the rest of the equation for us. So let's figure out how we did it. So this is a picture of my laboratory setup. And you will notice that on the right side of the picture, there is a microphone bolted to a stand, and I'm going to call this the red microphone. And over here is another microphone bolted to a stand, and I'm going to call this the blue microphone. Now, these two microphones are set a distance apart, and then I actually went and measured the distance from the very tip of the blue microphone to the very tip of the red microphone. And I found that that distance was 2.0610 meters. Okay, now I'm going to use those microphones to measure the time it takes for sound, for example me clapping, to arrive at the first red microphone and then continue to travel on to the second blue microphone. Now it's going to be a very short amount of time, which is why I am using a computer. So after an experiment where I clapped in front of one of the microphones, LoggerPro gave me a graph that looks like this. Now, if you take a look, you can see that the red microphone detected a pressure wave a split second before the blue microphone did. And actually, you can tell that, look at, when I clapped, my clap was louder for the red microphone than for the blue microphone because the amplitude is bigger. And that kind of makes sense. If I clap near the red microphone, you get a very big amplitude because the volume is very high. Farther away, the volume decreases or the amplitude decreases due to dampening. Now, to be honest, I am only interested in a very small wedge of the graph, the transition from red microphone to blue microphone. So I've blown up the segment that is of most interest to me, and you can see that in this portion of the graph, nothing is happening. I haven't clapped yet. But right here, the first pressure wave is detected by the red microphone. So I'm going to start measuring here, and it takes a little bit of time for the blue microphone to detect the very same pressure wave, my clap. And so if I stop there, LoggerPro is going to tell me that it took 0.005905 seconds interval between when the red microphone heard my clap and the blue microphone heard my clap. All right, given this information, let's run some math. I found that the distance from the red microphone to the blue microphone was 2.0610 meters. I found that the time it took for the sound to travel from the red microphone to the blue microphone to be 0.005905 seconds. Given this information, can you figure out how fast, or in other words, velocity, the sound traveled from one microphone to the next? Give it a shot. I'll wait. Okay, well this is how I did it. I know that velocity is also distance divided by time. And so I replaced distance with 2.0610 meters, and I replaced time with 0.005905 seconds. When I did the math, I found that the velocity of sound is 349.0262489. Then if I apply significant figures, I got 349.0 meters per second. Now, that's the speed of sound in my classroom during that day. Lots of things influence the velocity of sound in air. For example, the temperature influences how quickly sound moves through the air, and so does things like humidity. The best example I can give you is, do you know on a winter's day, very crisp, very cold, no water in the air, you can hear sound very, very well. But then on the converse, during really hot, muggy summer days, it just seems as like the sound is all dead. Well, scientists have made this measurement hundreds, thousands, 10,000 times, and there's a kind of some agreement that the average sound speed of sound is 314 meters per second. If the speed of sound is not given to you in a physics problem in my class, you can assume that the speed of sound is 340 meters per second. Well, that's great, but what does that mean? Well, here's Adam Savage of Mythbusters fame being very goofy.
Heavier than air.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
The simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that,
And my voice gets really low, although somehow I'm still funny. It's scientific!
Okay, so what happened to Adam here? First off, I would like to say that sulfur hexafluoride is very dangerous, and we're going to discuss why in a minute. But being more dense than air causes the sound going through Adam's vocal cords to move much slower, and therefore you perceive it as a lower tone. Being more dense than air has other implications as well. Now, when Adam inhaled the helium, being less dense than air, when he opened up his throat, his vocal cords, all the helium escaped and moved up and was supplanted by oxygen, and he could breathe. Sulfur hexafluoride, on the other hand, is 6 times denser than air. If you were to open up a balloon, all the gas falls to the ground. And that means that when Adam opens up his mouth to talk, he can push some sulfur hexafluoride out, but a vast majority of it sinks to the bottom of his lungs. The very next breath that he attempts to take, he can't take any more oxygen. And so therefore, if he's not very careful, he will suffocate. Now, before you ask, I know, you're like, why isn't Adam dead? I'm very sure that immediately after this shot, Adam stood on his head, so that all the sulfur hexafluoride would run out of his lungs, therefore allowing him to take oxygen back into his lungs and continue Mythbusters like we all love. Well, how does what we have discussed here apply to these? Pretty, right? So how do fireworks have to do with, what do fireworks have to do with the speed of sound? If you pointed out that when you watch fireworks, you see the flash first, and then later on you hear the boom, you'd be correct. Well, what happens if this situation would happen? What would it mean if you see the flash and then heard the sound at exactly the same time? It would mean that the firework was going off very, very close to you, because the light would take just about the same amount of time as the sound, meaning that it has to be very close.